Have you ever noticed how some apps just feel incredibly fast while others feel kind of sluggish? Well, a lot of the time, it all comes down to how efficient the code is. In this explainer, we're going to build a kind of mental ladder to rank code all the way from lightning fast to painfully slow. And trust me, this is a super important concept, not just for building amazing software, but for absolutely nailing those technical interviews and exams. So let's get started. So let's say you've written some code, and hey, it works. That's great. But is it any good? I mean, is it fast? You could, time it with a stopwatch, but that doesn't really tell you the whole story. What happens when you throw 1,000 times more data at it? What about 1,000,000? And that right there is the key. We're not really interested in the exact number of seconds it takes on one specific computer. What we really need to understand is the relationship, the pattern between the amount of input data, which we'll call n, and the time it takes for our code to run. That relationship is exactly what we need to classify. All right, let's start with the absolute best case scenario. This is the top of our performance ranking, the undisputed champion. This is the gold standard, the best possible performance you could ever hope for. If you can write code that fits into this class, you've basically hit the jackpot. This is called constant time, and you'll see it written as O of 1. Now, that looks a little technical, but it's simple. The O just means order of, it's how we classify it, and the 1 doesn't mean 1 second or one operation. It just means a constant amount of work. The task takes the same amount of time, whether you're dealing with one item or a billion items. It just doesn't care. And here's what's so important to get. The actual number of steps doesn't matter for the classification. Whether your code takes 2 steps or 5 steps or even 5,000 steps, as long as that number is fixed and never changes based on the input size n, it's still constant time. It is completely independent of the input. Okay, so from that perfect ground floor of constant time, we're going to take our first steps up the complexity ladder. Now, these next 2 classes are still incredibly good. I mean, really, really efficient. But they do start to depend on the size of the input. First up, we've got logarithmic time, or O of log n. The magic behind this one is that the algorithm gets to cheat a little. With every step, it throws away a huge chunk of the problem. Think about looking up a word in a dictionary. You don't start at page 1 and read every word, right? No way. You jump to the middle, and in one move, you've eliminated half the book. That's why logarithmic algorithms are just fantastic for massive, massive datasets. Next up is linear time, or O of n. This one is probably the most intuitive. The amount of work you have to do grows in a straight, predictable line right along with the amount of input. So if you double the input size, you pretty much double the time it takes to run. It's a fair one-to-one relationship. Now, this slide gets to the real heart of how we think in big O notation. We only care about the long-term growth rate. When n gets huge, I'm talking millions or billions, those little constants like +3 or +700 become totally insignificant. They're just noise. We only care about the part of the equation that grows the fastest, the dominant term, which in all these cases is just n. That's why they all get lumped into the O(n) category. Let's just put these two side by side for a second, because this difference is absolutely critical. For a linear algorithm, going from 1 million items to 2 million items means you're doing twice the work. But for a logarithmic one, that same jump might just add one tiny extra step. When you're building large-scale applications, that difference is everything. All right, we're moving up the ladder again, and now we're leaving the realm of what we'd call good performance. We're getting into territory where we have to start being a lot more careful. Welcome to the polynomial classes. So here we have quadratic, which is O of n squared, and cubic, O of n cubed. With quadratic, if you double the input, you quadruple the amount of work. With cubic, if you double the input, you're doing 8 times the work. You can see how this starts to get out of hand, and it gets out of hand really, really quickly. And this isn't just some abstract theoretical idea. A super common and important algorithm that's used all the time in things like computer graphics and scientific computing, matrix multiplication, is a classic example of a cubic time operation. And this is exactly why researchers are always hunting for new ways to make it faster. We have now reached the very top of our ladder. And trust me, this is not a place you want your code to be. Welcome to the danger zone. This is where algorithms become so slow they're practically unusable for anything but the absolute smallest inputs. This is exponential time, or O of 2 to the n. And you have to catch the wording here. It's critical. The workload doesn't double when the input size doubles. No. It doubles when you add just one more item. Think about that. That kind of growth is explosive, and it's completely unsustainable for pretty much any real-world problem. The defining feature, the thing you always have to watch out for, is that the input size, n, is sitting up there in the exponent. Whether it's 2 to the power of n, or 3 to the power of n, or even n to the power of n, you're in this dangerous class of functions where the performance is just going to fall off a cliff. So, we've climbed the entire ladder. We've gone from the ideal performance of constant time all the way up to the danger zone of exponential time. Now, let's put it all together and see the complete picture. This is the moment where it all clicks into place. We're going to rank these function classes and see the full hierarchy of efficiency. Seriously, this is the slide you're going to want to screenshot for your study notes. And here it is, our complexity ladder, ranked from the absolute best to the absolute worst. This table is the mental model you need to take away from all this. At the very top, our champion, constant time. Right below it, the excellent logarithmic and the very respectable linear time. Then we start getting into the questionable territory of quadratic and cubic, and at the very, very bottom, the one we always try to avoid, exponential time. You know, to really picture this, imagine a graph. The lines for constant and logarithmic would look almost perfectly flat, just barely rising. The linear line would be a nice, steady, predictable diagonal. But the lines for the polynomial and exponential classes, whoosh! They would curve upwards so sharply they'd look like a rocket launch, going practically vertical right off the top of the chart. Okay, we've covered a lot of ground. But if there's just one thing, one key idea that you need to burn into your brain for your next exam or that big technical interview, what is it? The number one thing to remember is this. It's a hierarchy, and being lower on that ladder is always better. As your input n gets bigger and bigger, your choice of which algorithm class to use will have a way bigger impact on performance than how fast your computer is. Your goal as a programmer is to always aim for those lowest, most efficient rungs on the ladder. The real challenge isn't just analyzing code that's already written. It's using this knowledge to design elegant, blazing fast solutions from the very beginning.